the second lecture of the strain silicon fundamental innovation advance. Here we're picking up where we left off last time and mentioned that the initial groundwork was laid at Cornell University. Part of showing this is to not only emphasize the model that we're talking about, but how an important piece of this story is that corporate innovations, in particular, corporate investments in research that are longer term, which generally don't occur anymore by IBM HP. I wanted to show how such investments affect even the chance of university research being higher yield. In other words, because these organizations were investing in R&D, they actually had overlapping influence on universities, which made government investments higher yield. And so, here I'm calling that corporate influence, right? Which is really wasn't defined by anybody, but it turns out that people that were participating in this, we'll call it the scientific commons, were composed initially of both post-World War II, initially of both corporate researchers as well as university researchers. And that's a direct, you can see the direct consequence of that on the ultimate innovation, strain silicon. And the way that started was through my PhD advisor. So Dieter Ast, who was a professor at Cornell, he actually spent summers in HP Labs, which is located in Palo Alto, California. And in the 80s, there was a lot of work on gallium arsenide ICs. That's because, silicon was cranking away, but people were looking at higher mobilities, and they wanted to figure out, can we, build integrated circuits from materials like gallium arsenide that had higher mobility, which generally translates, at a higher level, that physics goes directly into higher speed and lower power. So if you want to create products at the box level, let's say, that have, higher, more capability in calculating things at lower power, or just using more power and going even faster in calculating, then you want to advance electronics. And what that really means is down at the individual material level, it implies that you want higher mobility in the charges that are moving in the semiconductor. And gallium arsenide supplies is one 3,5 material, and these are called 3,5 materials because that's from the column 3, and this is column 5. And other materials like indium phosphide is another example. So what Dieter was doing at HP was seeing that people were interested in these kinds of materials. And when he came back, I created a characterization technique that was useful for looking at some of these materials and trying to find out how they could be controlled. At the time, one of the problems was that these defects called dislocations were causing various, or people believed were causing different threshold voltages in field effect transistors in gallium arsenide, and that made too much of a variance, and so the manufacturing was not very good. Now, in addition to Dieter having that and kind of sending me in that direction through mutual interest, Jerry Woodall used to be on campus, and Jerry was a IBM fellow. Now, in those days, IBM fellow meant that you take somebody who's been very effective at inventing or getting things done, and innovation done, and the idea of making them into an IBM fellow is to give them great latitude to do whatever it takes to create and innovate for IBM, including it's expected that you would be interacting with outside scientific commons, including universities. And in this particular case, he was visiting Cornell quite a bit during my PhD. And eventually, through another graduate student, we started to interact. And using, what we had done for looking at these dislocations in gallium arsenide, we started looking at the role of dislocations in these lattice mismatch materials that I have mentioned before, and I'll talk a little bit more about those. But just for this part of the conversation, materials were generally all silicon. That was the most popular semiconductor, and still is today the basis for all of the most of the electronics manufacturing at the chip level. Other materials like gallium arsenide were coming up, but are very, 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 very small in comparison. And then some people started saying, well, there's so much infrastructure going in for silicon, and the material, the wafers are so big, and the economies of scale are there. Can you put these together? And that brought up this lattice mismatch problem. And even within just a simple device structure, Jerry started speculating that, well, we don't know too much about these lattice mismatch materials, and we have to learn how to manage these defects. So it was really a basic understanding, but again, founded in the idea that these materials, if you could understand this defect formation and how to control it, which seemed impossible at the time, I might add, then you could build new things. There'd be so many applications. So again, if we look at our system here, and actually I didn't draw the little individual circles within here in this talk. I'm just using the solid colors to represent the size of the uncertainty. So again, notice how we're not infinitely bounded as soon as we start, really. Infinitely bounded would just be, oh, I'm interested in all sorts of semiconductors, or I'm interested in lattice mismatch semiconductors for only academic purposes. But if you look at what's really going on here, both HP and IBM are influencing this sort of pretty wide-bounded, but still bounded area of lattice mismatch semiconductors. It's not, the entire world of semiconductors. It's a particular problem that actually has many applications in integrated circuits. And again, this is wide and large, because if you could start to solve different issues within here and you add it to the other things that are known technologically, you could believe that there's enough elements in technology that the chances of hitting a good application within here, would be possible. So, for example, there's optoelectronic circuits and optoelectronic, electronic. They're subdivided into wireless and opto, and there's all these things here. But this problem is so broadly recognized as a problem that if you were to solve this, you feel like the chances of hitting a lot of these applications, or at least one of them, should be pretty high. Now, what was interesting at the time is in this early stage of fundamental innovation, in this particular case, I'm showing you the importance of the corporate investment in fundamental innovation that's overlapping with the university, both in Dieter going into industry and industry coming into the university. It was assumed that all of the same pieces at the beginning would be used for implementation. People actually didn't think much about implementation because of that. It was so assumed that this green thing was kind of not really in existence. And people generally would think only about, yeah, there's some sort of applications over here, and what are the missing pieces over here I need to research in order to make that happen. Now, this actually did have an influence. So, for example, Jerry back at IBM had particular ways of depositing this material. One method was called molecular beam epitaxy, which I learned about when I visited him. And later in AT&T, you'll see there's things called CVD, which, because AT&T manufactured things, I got to see that too. So there's different infrastructure, and of course, it was always assumed that the current business models were not a used term back then, just to show you how fixed they were. I mean, for example, IBM had a model, which is it, basically makes and delivers things to customers. There was no other thought process about only selling IP like IBM did later. or outsourcing and doing a completely different model. These just were not considered, in these early days. So, but it was involved in innovation process, in that, in the back of everyone's minds, you had these kinds of things telling you how it could be commercialized. Some of the early work when I went to AT&T. So after, right after Cornell University, I was recruited to go to AT&T based on the fact that we could control these defects. There was a fairly fundamental, significant thing I had discovered here, which I won't go into technically, but it caught the eye of those in the know at AT&T, and they recruited to me because they also recognized that lattice mismatch semiconductors had a wide application in the future if people could figure out how to control all that stuff. So when I went to AT&T, it's incredible. As some of you might know, a place that had pretty much invented most part or a lot of parts of most technologies that we have today in the internet and in computers and things like that. Of course, the most famous one is the transistor, the solid-state transistor, which started this whole thing off. But in general, it kept doing that in many different areas. And so, for that reason, they could recruit a lot of good people from. They like to recruit fresh out of school PhDs to come in and do research. And my first day on the job, the inventor of the carbon dioxide laser, which, remember, it was still fresh in everybody's minds, the different kinds of lasers being discovered was a big deal, came in and basically said that I was in his old office and had to, do something great. So it gives you an idea of the kind of pressure, even though it's research environments, and back then corporations looked a little bit further out. The pressure to actually come up with innovations was very high. Now, it would look very organized if I just took my fundamental advance that I did at Cornell University and started working on it right away. In truth is that just because I was doing a great project in AT&T, when you get into the management of a company, you don't necessarily just continue that work exactly. In fact, I was on a different project when I first went in there. It dealt with lattice mismatch, but it also dealt with something called phase instability, quite an advanced, complicated problem where we were trying to create germanium tin alloys. But it's a very interesting story of how corporations dealt with early fundamental innovation. We actually had success. Nobody had been able to make germanium tin alloys before. And so we were the first ones to make them with significant amounts of germanium in them. And the problem is that the band gap did not open up, so it remained a semi-metal. And the materials that, for example, this is deposited on a material, another 3,5 substrate material called indium antimonide. And those materials are very difficult to work with, and the band gap never appeared, which meant it wasn't good for optoelectronics. And so that was my first experience with, AT&T thought the research was fantastic. But, if you go back to our model, yes, we had advanced in the technology piece, but, there was no apparent market application. And so even though, again, implementation was kind of assumed, it didn't matter because this was completely dead as far as anybody can see. And so you could see that we're generally encouraged to move on, although it was encouraged through the fact that since you're supposed to be doing something great, which meant science and eventual impact, this was, drives you to other things. So actually during this time, because of the, knowledge that lattice mismatch was important, we kept that work going in parallel and decided to focus on silicon germanium. And the reason we decided to focus on silicon germanium is that it is a model system where you could learn a lot, and it turns out we got kind of lucky in the sense that it was also a key alloy and engineering between silicon and 3.5s. It wasn't lucky in the sense that there were no other alloys in that range that could be used to put varying degrees of mismatch in, because other materials tended to be either 3.5 materials, which were a little less, here we're working on silicon in general. Notice that germanium tin are column 4 and silicon germanium is column 4. We're trying to stay close to silicon because the idea was to advance silicon. Although very soon what I started realizing was silicon germanium alloys could be used to span the gap between silicon and 3.5s. And you could engineer with them. And that's really when we started realizing that silicon germanium was a key alloy. One interesting thing was that when I say space here on this view graph, it's an area that no one else at AT&T could pursue. It was kind of interdisciplinary. It was between electronics and materials, and was what I was really ideally suited for. So the combination of taking your unique skills and working on some problem that seemed to be important led us down this path. The other thing was a slow transition to AT&T, and in some sense this is kind of like later on we talk about the ecosystem, a little bit like when venture capital rushed in when it was clear that ideas that were kind of static or sitting in large corporations and kind of leaking out through universities, could be brought to the marketplace and great return could be had. Even though there's some negative aspects that could be happening, the revenues rushing in to pull things out, you can actually accelerate things temporarily. And that's what happened at AT&T. In a way, AT&T's new focus on revenue, because they had just divested, because they were a monopoly and the U.S. government made them split into a long distance and local phone company, there was actually a new focus on being a real company now. And so that killed germanium tin, like I said, because that the application was not going to be, there was not many applications, and so market was disappearing. And so that helped kill that. It also helped accelerate our product, because our research, because there was a lot of focus on wow, these guys actually might do something. If these materials could be tamed, something practical might come out. The other thing is that my colleague who invented strained silicon with me is Yahong Zi, and he came from another area, and that was really an amazing thing, because without going into great detail, we actually had different parts of the puzzle, and by working together, we made the first strained silicon demonstration pretty quickly. A little bit more on this lattice mismatch problem, just from a materials focus point of view. The problem with putting two materials together with different lattice constants, at first you say, well, why is that a problem? And it's really because the materials are deposited atom by atom. So here's a silicon substrate. I remember the overall idea was this would be the best use of lattice mismatch materials, because silicon is the sort of platform for modern electronics. And so as silicon were to mature, and remember Bell Labs looked 10, 15 years into the future, as silicon matured in some degree, if you could deposit gallium arsenide, which has great optoelectronic properties, you could have photonics merge with electronics. So silicon obviously was going to dominate the electronic world. And so this naturally be a topic at AT&T, because, well, it made electronics, it made silicon, but it was a telecom company. And so photonics had already penetrated, and people were laying fiber and using optics now for long-distance telecommunication. And so if you could make a chip that could process silicon and emit and detect light, that was pretty good. So more focus centered in on this application anyway. And so what you'd like to do is have this wafer. This is actually a silicon wafer, and you'd like to have it moving through a fab, let's say, And what you want to do is deposit gallium arsenide in particular areas and then make that into optoelectronic device, for example. So what happens is this silicon has a particular lattice constant, which I'll draw as little boxes. Just think of them as, if I zoomed in at atomic level, these are the little unit cells of the crystal. So little, you can imagine them as just little boxes with atoms, you know, defining the little box. And it turns out gallium arsenide has a bigger box. So when its atoms are, you know, fully relaxed at their native thing, and if I want to put this one on this one, there's clearly a problem because the atoms don't line up. And that's a problem because when the atoms come down, you know, they're coming from a vapor phase. And so they're all flying down, and they find their spots on the crystal of silicon. So naturally, when they first form, this thing is going to be squished. If you will, it's going to look like this, right? Because the atoms don't know what they're doing, so they come down and line up with the template. And then what they find out is, oh my goodness, I'm much more squeezed than I should be, and it wants to pop out and relax like that. Well, when it pops out and relaxes like that, it creates a defect in the middle, which are these black lines. So these black lines are dislocations. They can't end they cannot end in a crystal, and so what happens is you end up with all these, you know, defects threading up through there, and they make the gallium arsenide not very good for any application. And so the terminology is those are referred to as threading dislocations because they thread up through the deposited layer. Even though actually they're the same dislocation, for example, this thread, this thread comes down and it has a piece in the interface which caused the relaxation. So this is the piece you actually need because it allows the gallium arsenide to relax. But because the dislocation can't end a crystal, you know, this has to come back up again. And so what you have is this is referred to as the misfit dislocation. These black things that come up here are called the threading dislocation, but they're often the same dislocation. It's just that the part that threads up is referred to as a thread, and the part that's at the interface is called the misfit dislocation. So there's some basic physics here that need to be investigated, and of course this is a generic problem. So like I said, if you could put gallium arsenide on silicon, then presumably you could put germanium on silicon, and the number of applications you just have to understand for all this stuff is just incredible. So you could actually, if you could solve this problem, there is many applications that could result. So we realized that silicon germanium was the pathway to do this, and we studied dislocation, nucleation, and propagation in those materials because that was the key problem, as you could see from the last slide. You know, one of the interesting things is students always ask, oh, you know, like, did we do huge calculations or whatever? And there's always an iterative interaction, you know, as usual, between modeling and experiment. In a way, it's just another part of the iterative process within the technology circle, but you know, the different modeling and the different research experimentally interact with each other to further reduce uncertainty about the particular mechanism you're studying. And so what happens is the empirical relationships actually are the most important most of the time. You know, what depends on what and how, what direction does it go, and then you can, you know, with such simple models that reveal those empirical relationships, eventually you get down to a much more precise model, and that's kind of what we did. An idea of how you have to understand what's going on through experiment before you can model the measuring the threading dislocation density at low defect density in the previous view graph is actually quite a hard problem, and so we spent 6 months establishing that technique. And the reason I mention that is that in most companies today, spending 6 months to characterize a key parameter in order to make a huge advance. Even though the advance could be fantastic, you know, it's a rare organization. It's going to let you spend 6 months to establish that today. So this is the overall lattice mismatch between different semiconductors, and this is good because first of all it shows you why silicon germanium was important. It also shows you why, if you solve this problem, you could put a lot of different materials with a lot of different functionality into manufacturing on silicon. So what this says is that the lattice constant of silicon, you know, that square that I was talking about, you know, the base unit cell is 5.4 angstroms, right? And it gives you, in this, the sort of band gap shows what kind of light or energy it can interact with. It does other things too, but that's basically one of the things it does. And over here is germanium, which you'll notice is the same lattice as gallium arsenide. So if you can figure out in these alloys between silicon and germanium, so these would be the alloys in between, you can kind of use it to engineer different lattice constants across this. And if you could figure out how that all works, well, that would be the gateway to putting these materials on silicon and creating those integrated circuits, because you would have been able to get germanium on silicon of high quality. So the key thing is, can you span this and get high quality? Now it turns out that we were getting better results of germanium and silicon. We were almost doing this because we studied, we learned how dislocation is nucleate, propagate, and it told us, you know, it gave us insight to my key invention, and then we were able to demonstrate that. However, germanium was still not quite good enough for optoelectronic devices of gallium arsenide, and we had a management change, and so we needed to demonstrate something kind of quick. And this is where Yohung and I actually got together, because I had material that was out here that was fairly good, but you know, it wasn't out here, so we couldn't do the optoelectronic application. And so Yohung actually had been in a group in graduate school where some of the people had tried to create strained silicon. And strained silicon was in theory known for a long time, because in the 60s, when semiconductors were really rising and people didn't know anything about them, people put them under pressure and looked at how their band structure changes and all this sort of stuff. And from that, it was speculated that if you could have tensile straight silicon, then you could have very high mobility. And if you put silicon on silicon germanium and it was thin, you would actually get that strain. So one thing we could do is put strained silicon back on top of silicon germanium. So you would have sort of the silicon wafer. The magic that we did was relaxing this so it's at its equilibrium lattice constant and not have too many defects come up. You could put silicon back on top again, but because this had been relaxed to its larger lattice, then this one would be strained because it wants to be smaller, right? And so that actually causes the electrons in here to move faster. And that was actually, at the end of the day, an experiment to tell management that this was all important, but indeed it became the most important output itself. So we were able to take something like this and eventually go here. This is, by the way, almost pure germanium. You can think of it as pure germanium. It's only 4% off. So essentially this is germanium, and remember that's the lattice constant of gallium arsenide. So having such high quality, you can see there's no black lines threading up through here versus here we have all these black lines. So you can see that through this engineering, which is an amazing feat actually, because you're really, man is really controlling nature here to do things it doesn't want to do. And you're able to, in a pretty thin layer, actually have very high quality material on top of silicon. So at Bell Laboratories, we continued that work, and when Yohung and I did that strained silicon in the first set of samples, we actually ended up with the world's fastest electrons in silicon at the time. And very quickly we boosted it up even further. And so here's Yohung and I in the Bell Labs News. Now, Bell Labs News, you got to understand, for scientists, that's like being on the cover of a major newspaper or something like that. This was the, the pinnacle of recognition within Bell Labs. You can see this is like 1991. So that's when the aha moment is happening for our delay of fundamental innovation now, because it actually gets commercialized inside a real product in 2004. So here I am, with much more hair on my head than I have now, and this is a nice young Yohung Z. And so we had worked together to make this significant jump. Lower up here, but I wanted to point out that now, in terms of notice how the focus has really narrowed down to silicon germanium technically, right? Do you see how all that interaction, that iteration has narrowed that down? Also, by now, we're thinking mostly about AT&T ICs because that's the focus of the company. Now, there's quite a broad range because remember I said we did everything from electronics to optoelectronics, which is a huge, market application space. And like I said, corporate implementation was just assumed that, and really nobody thought about this, it was just assumed that if we had something important, it would be sent through this somehow and reach the marketplace. Just to point out that this process that I described, the iterative innovation process that we've talked about in this class, was really operating there, even though we didn't define it, at this time. Obviously, the iterative innovation model we're using was developed much later. But I wanted to point out how you can see that market application, implementation, and technology are actually all interacting. And so what I did was I emphasized certain things. So first of all, the event is that the electromobility is the highest ever observed in two-dimensional silicon. That's important because that's the thing that makes chips go faster. So you're kind of making that connection to the market application. The connection is shown in this square right here. We directly say that electromobility is important. That's what we're concentrating on because it affects silicon components. And components is general, meaning that, huge application space. We were using something called molecular beam epitaxy that I mentioned before to deposit these films. But notice the need in this article to say, but it can be easily adapted to chemical vapor deposition. The reason that's significant is that everybody knew that if you wanted to manufacture in high volume, you had to move to CVD. So clearly, this is not some ivory tower only because we're already thinking about how to move it to CVD. And then related to that is if you're thinking forward, because we're not making, full-scale integrated circuits, there's a lot of work to do. And so one of the promising features of this material, as it says in this box, is the ability to withstand high temperatures. And that's important because the only reason that's important, the reason we did that experiment, is to show that it could be processed, possibly in a silicon fab, so that it could become a product. So again, completely interacting with market application through the whole time. So let's stop there and we'll talk about the transition to MIT next. We'll talk about how the innovation naturally run its course at AT&T, but if you were going to follow the innovation through the iterative innovation process, it was time to actually leave Bell Laboratories. We'll pick this up the next time.